Am I audible? Okay. So this is a tutorial session, and I will just recall or basically some results, well-known results from the fixed point theory, or you can say not so many, few classical results. Some of them already discussed, but I want to give a basically broad spectrum of the fixed point theory. Means what are the other directions or like that one. So of course, majority of these stand basically from the fixed point theory background. So there is no need to just give the basically formal definition and other things example. But of course, as you know that what the mean by fixed point theorem. Fixed point theorem is that you can say it's a basically mathematical statement under which we have the guarantee of existence of a fixed point of a given map defined on a some non-empty set. Because we know that several examples from the literature, and of course there are so many examples still in the literature, they don't have a basically fixed point. For example, if I consider a just translation map, so of course this does not have a basically fixed point. So it means that so that's why we need some concrete statement, a mathematical concrete statement, so we can say the guarantee of existence of a fixed point. And of course, other time this uniqueness is also important. Is basically due to application, because in some application we need the uniqueness of a solution. Of course, in some problem there is no need of the uniqueness. For example, in the optimization problems, there is no need of the uniqueness. But of course, in the system of linear equation and some other differential equation, of course, the solution is unique. So that's why we need the basically uniqueness of the solution as well. So two important issue. One is the existence. So we have, for that we have a basically translation map. So because this does not have a fixed point, so that's why we need a concrete statement. If we have a fixed point, whether fixed point is unique or not, then again we have a basically another counter example, that is identity operator or identity map. Every point of this map is a basically fixed point. So these are the issues. So just as of course Professor Khamsi already told us, basically a lot of hidden secret, or you can say discussion from the literature. But of course this idea of the fixed point is basically a very old one, because as he pointed out that initially it was not basically in the form of a fixed point theorem, or you can say result, or even definition of a metric space. Of course, Frese introduced this concept, but systematic definition given by Hausdorff later on, maybe after maybe something 9 years or 10 years, 8 or 9 years. Same, initially basically Banach proved this theorem on a continuous function space, because he was not a mathematician, he was a basically computer engineer. Banach was not a mathematician initially, he was a computer scientist. So, but later on, Banach give that, of course, means once we have the notion of metric space, then we have this theorem in the particular, or you can say specific statement, every contraction on a complete metric space has a unique fixed point. So my point was here, this theory is basically very old, and we can see its basically presence in the work of French mathematician Henri Poincaré. And of course, again, he was not a basically a fixed point theorist or like that one, because his research area was something mechanics and mathematical analysis. So basically, he used or utilized this approach to study this kind of the problem. Okay, and as we know that this is one of the important branch in mathematics, modern mathematics, we can say. Reason is that due to the application, of course, mathematical part is very important. And we can say this is basically bridge between the pure and applied mathematics, because on the one side we have a very nice and very important and very deep result in mathematics. On the other side, we have a very important application in the diverse field of mathematics, even outside the mathematics, especially in the computer science, in the economics, and in other areas, even in chemistry as well nowadays. So that's why generally people now considering this subject as a bridge between the pure and applied mathematics. Okay. Now this basically just I want to recall a property that is topological property, means which is invariant under the homeomorphism. Okay, so such property is called the basically topological property. So fortunately, this property, fixed point property. So what do I mean by fixed point property? Of course, in general, we can say if every continuous map defined on a topological space has at least one fixed point or not. But in particular, we just state this property for non-expansive map, because every non-expansive map is also continuous map. So this is called, so a topological space is set to fixed point property if every non-expansive map has at least one fixed point. So whether this is a basically topological property or not. So answer is yes, fortunate. So so this is a basically just simple observation. This is a basically topological property. So suppose T is a basically my homomorphism from X to Y, and S is where any continuous map from Y to Y. And now consider the basically composite map here. So of course this capital F is basically T inverse ST is again a basically continuous map, because composition of a continuous map is continuous map from X to X itself, now self map. So so if x naught remains the basically fixed point of f, and if suppose x naught is the basically fixed point of f, y denotes image of the x naught under T, then f of x naught just operate at x naught both sides. So T inverse of ST of this. So T this T x naught is basically just we, but of course this is a fixed point, and now we operate the T both sides. So when once we operate the T both sides, so T inverse ST of this one is basically just T x naught, but this is identity, and now this is basically just my, I can say this is a y naught, because y naught is the image of x naught under T. So this becomes finally S of y naught equals to just y naught. And what was the basically this is, it was a basically continuous map. So it means that this ST of y naught, or means you can say S of y naught equals to y naught. So which shows that this y naught is the basically fixed point of continuous map S again. So once this continuous map F has a fixed point, then of course it is invariant under the basically another continuous. So that's why this is a basically topological property. Broadly, fixed point theory divided into these three major categories. Of course, one is the topological fixed point theorem, and second is the metric fixed point theorem. So basically, theme of this GAN program is on this category, metric fixed point theory, because we are dealing the results in the either in Banach space and metric spaces, not in the basically just topological or algebraic topology and topological space. Another one is the discrete fixed point theory. So these are the basically three major category of fixed point. So just I want to just state basically some very famous and fundamental fixed point theorem from these categories from the literature. So already, of course, Professor Khamsi already delivered the, of course, 3 talks in this direction on Banach fixed point theorem, then its extension like Cresty fixed point theorem, then later on, of course, now he will start the basically fixed point theorem for the non-expansive map. So this is a you can say very important for this GAN program and main theme of the GAN program. But here I want to recall basically some important fixed point theorem from the other categories, which is from topological fixed point theory and discrete. So these first 3 theorems basically belong to this first category, topological fixed point theorem. And of course, this is the first fundamental and first fixed point theorem in this direction, and later on these are the basically extension of the Brouwer fixed point theorem. So what is the basically Brouwer fixed point theorem? Brouwer fixed point theorem says that if we have a continuous map which is defined on a closed unit wall in a Euclidean space, or you can say finite dimensional Banach space, then it has at least one fixed point. This is very of course, this is very natural result, and of course here you see this basically result basically for the continuous map, because in the case of metric fixed point theory we have a condition for contraction, contractive, non-expansive. So here class of the map is basically in general very large, that is continuous operator. But of course For that we need basically some extra conditions. Of course, Banach space is here, finite dimension, and we define basically this operator on a closed unit ball. But there are some other statement of this theorem. Generally, people also sometimes consider closed bounded convex, closed bounded convex subset of Rn. But here basically I just consider this operator on unit ball, closed unit ball. So of course that is bounded by default and it is basically convex. So so closed is already there. So boundedness and convexity is just by the due to the definition of the ball. So that's why it is the same statement. Or sometimes some people say compact convex set of Rn. So compact convex again is the same thing, because in finite dimensional compact closeness and boundedness is the same thing. So anyway, so this is a very fundamental result which was proved by the Brouwer in 1912, and of course this theorem is very important in mathematics, but it has very nice application in the other branches. Especially if I recall the one famous application from the economics, because later on Professor John Nash basically utilized this theorem to prove the basically existence of the Nash equilibrium in the game theory and economic problem. And of course, you remember, so this is a Professor Brouwer and Professor John Nash. I think he died in 2015 something in New York, something, yes, 10 years back, yes, 2015. And so just basically he basically gave the existence of the Nash equilibrium in the game theory and economics problem. As yesterday Professor Imdad say what the equilibrium problem, it's a basically intersection of the demand function and supply function. So always we have some saturation, and that point is a basically equilibrium point. So this theorem was useful, and of course for this study he got the basically Nobel Prize, of course, in the economics. And then again, as yesterday in the opening ceremony I also pointed out, still this theorem is very important. People basically prove its most complex and generalized form, and to study the basically again generalized equilibrium or Nash equilibrium for the complex games and problems. So in 2018 ICM, which was held in the Rio de Janeiro in Brazil. So this professor from MIT, Constantinos, got the basically this Rolf Neumeier Prize, and of course this is the second highest prize after the Field Medal. So still people are basically working on this theorem, and even that time I met Professor Michael Atiyah, because of course he is also basically one of the field medalists, and later on he also awarded the Abel Prize as well. And just before his death, he also claimed that he proved the basically Riemann hypothesis. But of course, later on it was a false. So he again, when I met, and then I say, okay, I work in fixed point theory. Then he started with the fixed point theory in the topological groupoid, not in the Banach space or like, because his theorem is very famous for computation point of view. So and so this is a basically Brouwer fixed point theorem. And as Professor Imdad said, if we consider n equals to 1, so this is a very fundamental or basic result from in the real analysis at UZ level. Means if I consider C, means in place of Rn, n equals to 1 R, and if we consider any closed interval on R, then of course every continuous map has at least one fixed point. So this is basically my R, and of course if I consider C equals to some maybe 0 to 1 or A to B, doesn't matter, and if I have a map from C to C, of course this is subset of R, and of course closed, bounded, convex, no problem here, and this is a continuous map, then it says that T has at least one fixed point. So there are two proof of this one. One is a geometric approach, that is very obvious, and another is simply you can do the simple analysis. So in geometric, what we can do, just of course this is I think is the logo of our Gyan program. So proof is already here. We can see this is basically my identity function, and this is some continuous function. So if we have a basically identity map, and we have a continuous function from the same domain, then of course it will intersect the identity function at least one, and that intersection point is a basically fixed point of the. So this is very, of course, this is a basically picture from the very famous book, Fixed Point Theorem by D.R. Smart from Cambridge University, something long back, 1968, like that. So okay, on the funny side, I put this picture, but this is a very famous picture in the fixed point theory people generally use. Okay, so proof is already here. Whenever you have a continuous map, then that continuous map always, of course, on the same domain. Then at least it intersect this identity function at least one. So that's why it has a basically fixed point. Otherwise, analysis just we can do simple analysis. What we can define? We can define a some map from C to C again, and this is from again geometry. What we can do? So phi of x equals to just difference of this map Ix and minus identity operator. Just difference, or maybe I can say simply Tx minus x. No problem. So this is basically difference of the two continuous operator. So T is a continuous already, identity is a continuous operator, so that's why difference is again a continuous operator. So this is a continuous map from C to C, and if we see what is the basically just phi of A and phi of B. So this is T of A minus A, and this is T of B minus B. And map is basically my from A to B, close interval A comma B to A comma B. So of course this greater than equals to, because image will be either minimum A or maybe more than A. So that's why this difference is always non-negative. And of course image may be maximum B or less than B. So that's why we have these two signs. Okay. So if I consider the basically equality sign here, suppose this is a equality sign. It means that, or you can say phi of A equals to 0. It means that T of A equals to A, means this initial point is the fixed point. And suppose, so proof is over. And suppose again we have the equality here. So again basically T of B equals to B. So there is a fixed point of T. But on the other hand, if this is a basically strict sign, it may be like that. It means that we have a continuous map. On this initial point A, it is basically value is positive. On this point B, it has a basically negative sign. So we know that basically a very important theorem from analysis. I think so, intermediate value theorem. So if we have a continuous function, we change the sign between the 2 points, then it has at least one root. So it means that by the intermediate value theorem, there exists a basically you can say C, or maybe you can say Z in capital C, but not capital C, in open interval A comma B, because otherwise if it's same, such that phi of Z equals to Z. But what is the phi of G? Oh sorry, it has a solution or root. But what is the basically phi of Z? T of Z minus Z equals to 0, so T of Z equals to for Z. So again it is a basically solution. So either we have a equality side and still we have a fixed point, otherwise simple analysis. So proof basically idea again from the basically geometric interpretation. So this is very natural result. Okay, and it has a lot of application, but important thing is that whenever we give this any result in mathematics, we always try to extend the given result for the bigger domains or maybe more important spaces. Because my space is finite dimensional, so of course application of this result is limited. So question was whether we can extend this result for a infinite dimension or arbitrary Banach spaces or not. This was a question. So of course, and why these infinite dimensional Banach spaces are important? Because these space of the continuous function, sequence spaces, all are the infinite dimensional, and we can characterize lot of things using this one. For example, for the space of continuous function, we study the basically solution of integral equation and differential equation, and so many other things. For sequence spacing, we can characterize the so many compact operator and like these type of the things. So that's why these arbitrary Banach spaces are very important. So of course, answer of means in general, answer was no. So for that, I think Kakutani gave a basically one counter example in L2 spaces and you can say in the C0 spaces. So so this was a example sequence space just x equals to C naught, space of the all null sequences with supremum metric or norm, and if consider a closed unit ball in C naught and define a operator from P to B, something like that, T of x equals to, so x is basically sequence, so this is something 1 minus mod of x1 comma then x1 x2, so okay. And then so this is a simple exercise because this is a tutorial session. So now we prove that norm of Tx minus Ty equals to norm of x minus y, where of course for all x and y in B. Say isometry. So can we do it? Yes, maybe quickly, 2 minutes. Okay, this we give the basically this is a continuous map. So because I want to check whether a continuous map on a arbitrary Banach space or infinite Banach space has a fixed point or not. So we already consider this is a basically closed unit ball and convex. Only just this is enough. Of course, there are several ways to check continuity. We can also go through the continuity from here, but from here it is very trivial because since this is isometry, automatically it is a continuous map. Similar example in the L2 spaces. Similar example in the L2 spaces also here. With respect to supremum norm is there on C naught because this is a Banach space with respect to supremum norm. Of course, this is exercise from the book of Hamsi. Again, an introduction to metric metric and fixed point theory. Introduction to metric space. This is a very important book. So if you want, then I have a copy of this one, so maybe I can. Otherwise, very expensive book. I think maybe something 12,000 or 11,000 like that. Is it okay? Okay. So because this is a non-expensive or isometry, we can say also. So this is a continuous map because every contraction I see, every isometry, every non-expensive, all are the continuous map. Okay, so this is a continuous map and which is defined on a closed and bound ball. Suppose if we assume that this has a basically a fixed point, means Tx equals to x, then we have a contradiction to this fact 1 minus mod of this one. So if we assume T has a fixed point, then we lead to this contradiction 1 minus mod of x1 equals to 0. Just because we compare the coordinate from both sides and we will get the basically this contradiction, this part. It means that of this and this is not on the. So anyway, a similar example on this one. So question is that how we can extend this result for arbitrary Banach spaces. So of course, yesterday as I pointed out that we want to extend the class of operator from contraction to contraction, but on the time we reduce the basically space from complete to compactness. So in Soder in 1930. Basically, he just basically give the means extend this theorem. So basically, in place of the this closed and bounded ball, he considered the compact subset of a Banach space. Because in R, compact and closed and bounded is same thing. So that's why. So just if we put this compact, that's why basically here I just put the basically this word only closed and bounded. Otherwise, some author put the basically compact here. So if I put the compact here, then you say, sir, what is the difference here? You already take the compact here and in the same. So basically, this is basically close and bound is better. So what we can do? So now this is a basically compact because generally in infinite dimensional Banach space, ball need not be basically compact if you, because it's of course always a closed and bounded and convex, but that is not basically compact. So that's why this is a basic. And this theorem has lot of important means application, especially in the differential equation side. To show that basically exists, and Professor Dhage is here. I think you also utilize this theorem several times in your basically existence results and like this. So this was a very important theorem. Okay. Uh, Professor Amin already discussed this part, so I am not going to this part. But and of course now tomorrow he will discuss these two theorem, because just today he I think stopped here, maybe on the Gaude theorem, because I think till now he did not mention the basically Kerr theorem about the normal structure and reflexivity. So only just he stated non-expansive map, because class of the non-expansive map is bigger than contraction, as we know that, but there is no guarantee of the fixed point of a non-expansive map. For example, like translation map again. So that's why we need some concrete statement which gives the basically guarantee. So of course these theorem will be basically discussed in the coming days, in three coming days. So that's why I am not going to discuss these theorem. But I want to just basically so I just basically here point out the third category, that is the discrete metric fixed point. So this is the man Tarski. Basically, he basically proved without any just metric and underlying topology. Just basically, this is the discrete version of the, or you can say discrete analog of fixed point results. So what basically he proved? Okay, he considered the basically complete lattice, and it's a basically F is a order preserving map. No continuity in this one because we don't have any topology here. So just why this order preserving map means x is less than y, means whatever the order there, and then of course f of x y length. Then set of fixed point is of f is basically non-empty, and even that is also a complete lattice. So this is very useful in the computer science and other area in the mathematics. As we say that of course we always interested in the you can say generalization extension. So on the other side, so these all theorems basically. And of course, after that, this order, after that, Tychonoff basically extend this theorem's order to the locally convex spaces, that is more general spaces. So this is basically another important generalization and very useful in the other areas. Okay. So as I said, we always looking basically just to study the theorems or problem in the more general setting for more general operator. So that's why fixed point theorem for the multi-valued map is also very important. So this is another research area. So this theorem, Banach fixed point theorem, is already extended for the multi-valued maps, because multi-valued maps describe the lot of problems from economics, from the game theory, from the computer science, from the fractal theory, and differential inclusions in the differential equation. By differential equation, but we have the containment that is called the basically differential inclusion problem. So that basically is studied by the basically multi-valued map. So for the multi-valued map, we have a of course total means complete side of the story. So, but what I want to say here, just this Banach fixed point theorem already extended to the multi-valued map by the Nadler in 1965. And one very important here, because Khamsi was saying 1965 revolution. So this was not the basically revolution only for the non-expansive map. Lot of important results appeared from 62 or 63 to 72, like Eldestin theorem, because from Banach theorem was proved in the 1922, and after 1922 Eldestin proved his result in almost 62 and 65, and then theorem, Gaude theorem, Broder theorem 65, and this Nadler theorem in 1969, 69, and then so these 10 years were very productive, or you can say. So that's why. So Banach theorem basically extended for the multi-valued maps by the Nadler, and of course later on in fractals, that theorem is very useful to generate the basically fractal. Collet theorem is there. So people from the computer science, so you can generate the attractors or you can say fractals using the Collet theorem. So that is total application of the Nadler fixed point theorem, multi-valued version of the Banach fixed point theorem. Okay, and so now if I come to the basically non-expensive part, so of course Browder theorem is also extended or proof for the multi-valued map. Lim is basically give the basically extension. And of course, this theorem will be discussed in the coming days, but for the Kerr theorem, this problem is still open problem for the multi-valued map. So this is very important problem still. Of course, there are some partial answer in some particular specific setting given by the people from the University of Sevilla, Spain, or some Polish mathematician, but still this problem is open for the multi-valued map. So this is a very important problem. So what is this? This is a Kerr theorem. If we have a non-expansive map which is defined on a closed bounded convex subset of a reflexive Banach space with this geometric structure that is called a normal structure, it has a basically fixed point. So still this problem is open in this area. So this is another problem. So of course we have to think about this problem. Just if I can 3 o'clock. So, just I stop here. Another important thing, uh, Professor Khamsi explained, or you can say talked about lot of things about the Keresti theorem. I think maybe 10 times in a day or maybe 15 times like that every time. And of course, I have a one book. Depend. We are you can think again same thing as I mean say that just I want or want a different proof of the Banach theorem. So let's open the door and after that story is there. So same thing that proof is also very natural by given by the Chirich. So I stop here because we have to go to university visit just for a few hours, maybe 2.5 3 hours. So now I stop here and tomorrow we will continue.
Two quick question.
Yes.
Where we can found the proof of Brouwer fixed point theorem.
Which one? In general?
General. Yeah.
Yeah, in the one proof is L for R equals to 2 is given in the basically DR Smart book also. Yes.
For general RM for not restricted.
Of course, in his paper, but I cannot say in general.
So this is every
So,
time people usually say that Brouwer fixed point theorem is one of the first fixed point theorem, but I believe that almost everywhere nil. People don't know the proof for a general setting, so
general setting is very
we
different.
all should look at this. As the research is still on,
No, in TVS proof is given. In topological vector space setting is proof is available.
There is a one very interesting remark by Sheeper.
Sahipat.
70 years of Broward fixed point theorem, and then 90 years of Broward fixed point theorem.
Even I think 100 maybe.
And 2014, there is a one proof given by Professor Sompom Dompolsa, a shorter proof of Broward fixed point theorem. Another proof given by Hisham bin Makhail, a shorter proof of Broward fixed point theorem. So it's so profound, even though I was discussing.
So that's why I say na, so,
even myself did not see the proof of Broward fixed point theorem.
original.
I was discussing with him. Did you see? So he was saying no. So at least because we are the fixed point theory people, we should see the proof. It is a different ball game. It is understandable to us or not, but at least we should see. Oh, this is the proof for general.
It is in finite dimensional spaces.
Yeah.
So it's not good. It's not finite dimensional space.
No, that's a different but he is asking whether we have gone through the proof or not.
But
it is difficult for high dimension. R1, R2 are okay.
Yes, up to R2 using the simplex and this one proof are available.
For R and
Algebraic topology and so on. So it requires.
Please see the proof, generic proof. You all should see at least one margin.
So this is a part of research. Okay, this is a one proof, may be difficult, but people came with a different idea, as he mentioned. The Sahi Park and others, Hashem and Sompong, they came through the different. So for example, as I Chiric also proved obviously this Clasical theorem just using 100% analysis, no algebraic approach. So this is also part.
So there are any generalization of order fixed point theorem to fixed space or a small class of complex space.
Yes, there is basically generalization that is known as the Darboux fixed point theorem. Yes, because there we relax obviously this compact, because of course compactness relation is very hard. So this is generalization, that theorem is known as the Darboux fixed point theorem, and that is very useful in the differential equation.
Great, ask the question.
Using measure of non-compactness. Yes. They basically reduce the this compactness.
Narendra bhai, you should ask something.
Again, there is one
You
more
are asking here, so we can ask.
But your question was not the question, it was the information.
But it's very exciting book. Only 2.5 page by so formal. And Hisham is more difficult.
More.
सर यहीं पे रखूँगा
क्या